Alright, so in the last video, we've actually seen how the reduced echelon form um, work, and that each column or each column has to have only a leading one, and each row has to um, have a leading one, and each column has to have the leading one has to be the only non-zero variable, non-zero scalar in the column. Uh, So with knowing the number of solutions from the matrix is quite straightforward. If you have a matrix like this where you have a leading one sufficing all of the rows, then you would simply have a single solution. Otherwise, if you have an all zeros row, then you would have an infinitely many solutions. Otherwise, you'll be left with if you'll be left with a no solution whatsoever. Like when you have um, when you have some sort of when you have a row that really doesn't equate the right hand side, then you basically got a solution. Now, there's something else to note. A matrix where most of its entries are zeros is called a sparse function. Not all of its entries, but most of its entries are zeros is called a sparse function. And there's something else that I wanted to show you here before we proceed to the very end. You can see here that the reduced echelon form does not necessarily mean that you have one right below the other. Each leading one is immediately below the other one. It could only mean that each leading column or row is one, and for that one, all of the rows above and below it are zeros. Just that. Okay, moving forward now with the what we have left. So this is sparse function. Now, we've got some decent examples that we could actually study. You can just take a look at this like really quick.
And welcome to YU Elimination. Gauss-Jordan elimination. In this lecture, this application involves modeling and predicting with arrows showing the direction and 92 east. The student
So
the
you kind of form this equation.
and traffic flow into the south intersection. Let's see how this system of equations can be solved to find the values of the to the vertical line or all zeros. The contour represented as a matrix, that matrix can be transformed with either one of those rows. To be in reduced row echelon form, all the entries below that leading entry must be zero. Since all the entries below the second row's leading entry are again, there is only a single non-zero entry. So we zero that entry using a pivot to add negative leading entry are now 0. We move to the fourth row, making sure that its leading adding -1 times row 5 has now become all zeros. Rows containing all zeros, every entry above each leading entry must also be 0, and 2 of these entries are not 0. Starting with the non-zero, we move to the leading entry of the third. We also saw, when writing parametric equations to describe these solutions, the variables associated with pivot, and then rearrange the equations so that the dependent variables are alone on the left side. This gives us equations that express the dependent variables x1, x2, x3, and x5 as functions of the free variable x4. We then equate the free variable x4 to a parameter that we will call t, and replace x4 in the remaining equations with t. We now have a set of parametric equations that express all 5 system variables x1 through x5 as either constants or functions of the parameter t. traffic flow measurements at of values which you cannot can valid value could not be a matrix representing we knew a vertical line was a pivot column. In particular, x4 was a free variable, which could have many possible values. And as we saw, depending on the value of x4, the calculated values for x1 and x3 varied. So what if we made an additional measurement to determine the actual traffic flow at x4? What effect would this have on our system of equations? To find out, let's go back to the simplified equations created from our original traffic model and plug in a value for x4 equation, either one line or all zeros. Only one row entry is a 1. Since that entry is a 1, we once again make sure that the entries below are zeros. Only one of these entries is not 0. So we use a pivot to add -1 times row 2 to row 3. All the entries below the second row's leading entry are now 0. So we move to the third row and check its leading entry. Since that entry is a 1, we make sure that all the entries below are zeros. Once again, only one entry needs to be zeroed, and we do this using a pivot, adding -1 times row 3 to row 4.
Right. Third polynomial functions could be used to determine the relation between x and y. Third polynomial functions. This is an interesting thing. I don't remember this. Surprisingly, I don't remember any.
Any value we pick for the parameter t will produce values for the coefficients a, b, c, and d in our polynomial. Now the leading entry of every row is a 1.
Earlier we've talked about finding the inverse of a function by solving to make it an identity matrix or applying Gaussian relation in matrix of any matrix next to it. Any matrix will be converted into an inverse. An example. Interesting. You could actually get the inverse of a function from it. This is something I'm not really sure what I've seen.
Any value we pick for the parameter t of linear equations with multiplication could a given set of data points. Given a group of points, we will try to find a curve whose graph passes through those points. In these examples, we will use a curve described by the function ax cubed plus bx squared plus cx plus d, where a, b, c, and d are constants which determine the exact shape and position of the curve. An equation of this form is called a cubic or third-degree polynomial equation, since the highest power to which x is raised is 3. In the real world, an equation like this might describe some sort of physical system. The quantities x and y could represent the relationship between any two measurable quantities of the system, such as the temperature versus pressure in an engine cylinder, or the number of gazelles in a wildlife preserve versus the number of lions, or the amount of money invested in the stock market versus the amount of coffee drunk by investors. So let's say that 4 measurements are taken of a system described by a third-degree polynomial function. Given the x and y coordinates of these 4 data points, how can we find the values of the 4 constants a, b, c, and d, which determine the shape of the curve that passes through those points? Cubic or third-degree polynomial equation, since the highest power to which x is raised is 3. In the real world, an equation like this might describe some sort of physical system. The quantities x and y could represent the relationship between any 2 measurable quantities of the system, such as the temperature versus pressure in an engine cylinder, equation with 4 unknowns a, b, c, and d. We also have 4 different sets of values for x and y which we know satisfy that equation. If we substitute these values for x and y into the equation, we can create 4 different valid equations where the unknowns are a, b, c, and d. Matrix form, changing the first row's leading entry to a positive 1. We will do this using Knowing these coefficient values, we can now graph the function, either by plugging in various values for x and calculating the corresponding y values, or by using a graphing calculator. Single unique solution for the system, we know that this is the only third-degree polynomial function that passes through these 4 points. But we have seen that sometimes systems of equations can be inconsistent, having no solutions. To see how this can happen, let's take the same 4 points as before and move 1 point so that it is positioned directly under one of the other points. Now we have a configuration where 2 of the points have the same x-coordinate. 5 from each of 4 and reduced. In fact, it is impossible for any curve that passes through the functions. This tells us that there are no values for the coefficients of this function that are consistent with these 4 data points. In fact, it is impossible for any curve that passes through these 4 points to be a function of x, since that curve would not pass the vertical line test for a function. So far, we have seen that when curve fitting a polynomial equation to data points, the system of linear equations generated by this problem can have no solutions or a single unique solution. But is it possible for the system to have infinitely many solutions? Let's see what happens when we are given only 3 points. Function. This equation, the house tree to 2 times 1 multiple lone form, all the other entries in every column containing a leading entry, throwing the only non to add -1. Second row's combination, since only 3 of the 4 columns to the left of the vertical line contain a leading entry, there are only infinite columns are remaining 2 rows left that a free variable d equations of a functions -3, -1, and 4 for a, b, c, and d. Up and 2. 0. A unique third-degree polynomial function and graph that includes these 3 points. So far in these lectures, we have studied different applications of linear functions and have seen that these functions are graphically represented by straight lines or surfaces. In the next lecture, we will introduce quadratic functions whose graphs are parabolas.
Alright, so that was basically the everything that we needed to cover. And the next step we should be studying about slopes, and then we should move right into fast AI. So next week should be fast AI and vectors, not slopes, more like vectors. I think we've covered a pretty good chunk, and this set of information would only stick if we do like practical stuff on using these, and we should do a lot more of this. I'm not sure how we could practice more of this. Maybe we could program things out, but we could get acquainted with NumPy. NumPy has a lot of features that basically the core of it is to use matrices, and it enables you to use matrices however you like and however you want. Alright, so this is it for this video. We'll see you in the next one.